Welcome back. This is part 4 of atoms, molecules, and ions. And in this part, we're going to look at the periodic table, and we're going to look at how we classify groups based on where they are located in the periodic table. So this is the periodic table, and this was designed early on, and there were some gaps in it, and they kind of figured out what should have gone in certain areas, and that's how they found out that there were these common characteristics of different things based on the properties. And so what they did, I didn't do it obviously, was that they put them and arranged them in so that it would make sense. So elements are arranged in rows, which we call periods, okay? So they go across or horizontal, and then vertical columns are groups or families, okay? Elements in the same group, that is the column, have similar physical and chemical properties, and they can be categorized as metals, nonmetals, or metalloids, and we have those in certain areas as well, so we can kind of keep an eye on them. So a metal is a good conductor of heat and electricity, just like you think of iron or other metals, and a nonmetal is a poor conductor of heat and electricity. So sodium chloride or chlorine gas, those are nonmetals, and they don't conduct. Metalloids have properties of both, and so they're kind of in between a metal and a nonmetal. And so we have those on the periodic table, and I can kind of show you where that is when we look at the more advanced look at the periodic table here in just a minute, the other figure. In this, what we're showing you is that you can see the different groups. And so these groups, and you should know what they are. So this is group 1, okay? And these are the alkali metals. Group 2, which are the alkaline earth metals. And then over here, we have the chalcogens, okay? And then we have the halogens, which are, this is 17, 18. And then 19. The noble gases are in this final one, okay? So we can say that everything in this group and will have the same characteristics, everything in the second group, and then the same for the others. Now, these are what we call transition metals. So these are going to be these are going to not really follow nice logical little rules all the time, and so that's why we look at those actually separately. So let's look at a little bit about mass scale and average atomic mass. According to international agreement, an AMU, or atomic mass unit, is defined as equal to 1/12 of the mass of a carbon-12 atom, okay? And so since everything is set from that, then the atomic masses are basically ratios compared to carbon-12. Carbon-12 is like super abundant in the world, and it's like the major part of our bodies, and so that's why they kind of decided that. So experiments have shown that hydrogen is only 8.3985%, whatever, as massive as carbon-12. So if the mass of one carbon-12 atom is actually 12 AMU, the atomic mass of hydrogen is 8.3985% of that, or 1.0078 AMU. So everything else is done like that too, so that we have the proportionality of each one. And so again, that's why carbon-12 is like 12.0 basically, and then everything else is how it's in proportion to carbon-12. I wanted to show you something on this. Now, here you see again the atomic number in this periodic table is going to be that top number, and it has no decimal places, whereas the mass is going to have decimal places. All right, so that's kind of how you tell the difference there. Sorry. All right, something I want to show you. All right, so I wanted to show you that this is the metal versus metalloid line before we go any further. So, okay, that can just stop doing that anytime. All right. The line goes kind of like this. See this jagged line? Okay, so that you have the metalloids in the kind of the yellow color, and the blue are non-metals, and then the green are metals. Hydrogen actually has properties of both, and so you may see hydrogen depicted on either side of the periodic table. So if don't get confused by that. So all of these are metals on this side. All of these are non-metals. Notice there's not that many. And then these are the metalloids, the ones that they're showing you here. And we say that they follow this kind of squiggly line. It's important that we look at main group. Okay, the main groups, which are groups 1 and 2, and then 14, 15, 16, 17, and 18 are your main groups. That means that they pretty much follow the nice rules that we have. But like the transition metals, which are in this area, and then the different series that are down here, don't always follow that. So that's why we differentiate. So when you look up the atomic mass of carbon, we said it's 12.01 AMU. Not 12 like we learned the number was set earlier. And that's because that there are naturally occurring isotopes of carbon, just like there are naturally occurring isotopes of other elements. And so the atomic masses in the periodic table that we see, and the reason that they have decimal places is because it is the average atomic mass of those that are found occurring naturally. So the ones that we see in nature. So the term atomic weight is sometimes what we're referring to as the average atomic mass. So, and the way that we come up with that is that we take the percentage of carbons that occur at 12.0000 AMUs, and then there are some others that are 1% naturally occurring that are 13.003355 AMU. And so when we look at that as a weighted average, it comes out to be 12.01, because in nature doesn't always follow the exact little rules that we try to set up for it. So that's why that's kind of a discrepancy, if you will, when you look at it. So, and the way we come up with these actual masses is we use something called a mass spectrometer. And a mass spectrometer determines this abundance of isotopes. And so like it'll give you a readout so that you see that 90.48% of naturally occurring neon is neon 20. And then only 0.27% of naturally occurring neon is 21 mass. And then 9.25% naturally occurring neon is 22 AMU for the mass. And so when you plug those in, you calculate the average atomic mass that you'll see on the periodic table. So in this example, Oxygen is the most abundant element in both the Earth's crust and in the human body, which is why we look at it a lot, and it's involved in a lot of reactions. The atomic masses of its 3 stable isotopes is oxygen 16 at 99.757%, oxygen 17 at 0.038%, and oxygen 18.205%. So it's 16, but it's really, if you, as it's measured by the mass spectrometer, is 15.9949. The 17 one is 16.9991, and then the one that's 0.38% is 17.9992. So to calculate the average, okay, what we're going to do is, and I'm going to write it how I normally do it, and I like to set it up this way just because it's a little easier to follow. Now, if you follow this fine going across, that's fine. But what I like to do is I like to write it like, okay, so I've got 15.9949 AMU, and that's times 0.99757. That's 99.757%, and that's going to equal 15.9549 AMUs. And then the next one, which is 16.9991 times, and you got to really watch the percentages when they're small like this, 0.00038 is 0.038%, and that's going to give us 0.0065 AMU. And then last but not least, 17.9992 times 0.00205 is going to give us 0.0369 AMUs. And then when I add those up, it's going to give me 15.9983 AMUs. And if you look at the periodic table, you will see that that is the number that is listed as the mass of naturally occurring oxygen. So that's how you get this number. So you can't just look it up though, you've got to show me your work. That way I know that you're working it. And so here is your for practice. So you should be able to do the same thing I did. Copper 63, copper 65, I gave you an easy one, it only has 2, and calculate the average atomic mass of copper in the world. All right, thanks again for staying with me, and I'll see you again for part 5.